Okay, so lesson one just introduced what vectors are, and so we've got these new mathematical objects that aren't just numbers anymore. Ooh, I flipped back to lesson one. Sorry about that. And now we're going to learn how we can maybe define what will it mean to add two vectors, what will it mean to subtract two vectors. And then the first kind of multiplication we're going to learn is multiplying a vector by a scalar. What will that mean? So 5 times a vector, what's that going to mean? And everything we do in this lesson is the geometric interpretation, so being able to understand what it looks like with the arrows drawn out. In the next lesson, we'll see what it looks like to kind of represent this algebraically so that we don't have to necessarily draw the pictures anymore, which will be a nice change. So here's my introduction to this idea. So let's say that you're in a plane and the plane wants to fly from A to B, we'll say. But we'll say that there's a wind blowing, and the wind's blowing about that fast in that direction. So which way would they have to point the plane in order to actually end up on a course that would end at B? So how that works, if the wind's going that way, they're going to have to point out this way, some way. I don't know if you can see that cursor, so I'll draw. They'll have to point out kind of in that way so that the wind knocks them back on the path back to B. And so the way I do that is I draw the wind ending at B, because we don't need to, vectors don't have a location. I can draw it wherever I want. So I'll draw the wind ending there, and then I'll point out to the tail of that wind vector, and that would be the way that the plane needs to point so that the wind knocks it onto this path. So that vector that is the combination of those two is called the resultant, and in this case we're talking about the velocity of the plane. Here's the wind velocity, and here is the sort of what's called the air velocity of the plane. So that would be the speed of the plane and the direction of the plane if the wind wasn't blowing at all. And what we have is, so the air velocity, what the plane's trying to do, added together with the wind equals the resultant velocity. And that sort of gives you, so our first sort of geometric interpretation of what it's going to mean when we add vectors. So if I add this vector here, the air velocity, to the wind, the answer is this vector here. So when you add two vectors, you get a new vector. And the key thing here is these two vectors are drawn what's called head to tail. So the head of one and then the tail of the other are touching. So to add vectors A and B, draw A and B head to tail, and the addition of A plus B is the vector that connects from the start to the end of that path, is how I'm going to write it. So if I have a vector A and then a vector B, maybe I'll switch colors. So I've drawn B at the head of A, head to tail like that. If I was going to add those two vectors, I would get this new vector here, which would be the vector A plus B. That's our first definition of what it's going to mean to add vectors. So when you add two vectors, the result is a different vector. The next thing we're going to look at is scalar multiplication. So I'm going to think about what would it look like if I did 4 times the vector A. Well, to figure out what that means, we'll remember back in elementary school when you first learned to multiply, when you did 4 times 5, you might have thought of that as repeated addition, 5 plus 5 plus 5 plus 5. So that's how scalar multiplication gets introduced. We think of it as A plus A plus A plus A. So if that's A, 2, 3, 4 A's. This vector that goes from the start of that to the end of that would be the vector 4A. And basically what that means is it stretched that vector A out 4 times as long as it was before, but keeps the direction. If I had something like negative 2A, well, I'd try and draw like an A and an A, but the negative is going to flip their direction. So I'm going to flip them so that they're going the opposite direction. This thing would be negative 2A heading in the opposite direction. So these would both be minus A's in that case to go the opposite direction. And so scalar multiplication stretches the vector. It either keeps the direction exactly the same or flips it if the scalar is negative. So 5A is the vector that's 5 times as long as A, but in the same direction as A. Negative 3A is a vector that's 3 times as long as A, but in the complete opposite direction of A. That's kind of the idea with scalar multiplication of vectors. And if we know how to add vectors, and we know how to multiply by scalars now, we should be able to subtract vectors. So if I wanted to learn what A minus B was, it would be nice if it should look something like this, A plus negative B. That's how addition works. That's how subtraction works with numbers. So it would be nice to define subtraction for vectors in the same kind of way if we have understanding of what everything. So that's going to be our definition. So if I have the vectors, say, A, and we'll say B going this way, if I wanted to subtract those, I would draw A, and then I would draw negative B, so B in the negative direction. So going that way, and I would get this vector. I wanted a different color. I would get this vector, and this vector would be A minus B. So that's one way to define subtraction. The other way, the other way to get this exact same vector is instead of drawing B backwards, still draw it forwards. But instead put the vectors tail to tail. So instead of drawing them head to tail, when you're subtracting, draw them tail to tail. And what you should see is that resulting vector that we got here is equal to this vector on the other side. So this is also A minus B. And so what we've done there is we've drawn them tail to tail, and we've gone from B to A to do A minus B. So I'll write those instructions out. To get A, subtract B, draw A and B from B to A. If you connect them the other way, you actually end up with A minus or B minus A instead. If you connect from A to B, you're getting B minus A. So you go from the second vector in the subtraction to the first vector in the subtraction, is how we sort of geometrically represent vectors. And so a pretty popular diagram is what's called the Parallelogram Diagram. So this it's actually so popular that so if you take something relating to vectors in university, it's called linear algebra. And so my linear algebra textbook, which I think I still have in the closet in the classroom, you can ask to see it, has this picture on the cover. This is how kind of fundamental this picture is to this topic. So what you do is you make a parallelogram with these two vectors. So you just make sort of 2 copies of A, 2 copies of B, form them into a parallelogram. And then that parallelogram, its diagonals are 2 important vectors. So this one there, that is the vector. Well, it's going from A and then B, drawn head to tail. So that's the vector A plus B. And this diagram demonstrates that A plus B is actually the same as B plus A. If you go along the bottom, then along that side, you get the exact same thing. So it's showing that addition is the same forwards and backwards, which is a pretty important property of addition. We have that property of addition of numbers. We also have that property when you have addition of vectors. And that property that says the operation's the same forwards and backwards. It's got a fancy math name. It's called the Commutative Property. So you can put that one in your back pocket. The other diagonal that's connecting the 2 vectors drawn head to tail. So if I put the arrow going this way, I'm connecting from A to B. So from A to B would be actually, that's the vector B minus A. And if you connect the other way, from B to A, that's the vector A minus B. And what that's showing is A minus B and B minus A are opposite vectors. They're the same size, they're just off by a negative. That's another that's a property we have of addition as well, or subtraction with regular numbers. 2 minus 3 and 3 minus 2. They're both 1, but one's positive and one's negative. They're the same size, they're in opposite directions. Okay, so with all that, you can go ahead and try these ones. I'm going to take them up in this video so we can see what they look like. So for the vectors drawn to the side, draw a single vector that represents each of the following. So we're going to try and represent A plus B and then subtract C. So there's a few ways to do that. So again, you can pause and then come back and watch me do it. So I'm going to draw A and then B head to tail. So something like that. So there's a few ways to now do the next part. So this is the vector A plus B. And from that, we're going to subtract C. So what I could do is draw C tail to tail with that vector. And then if I want to do subtracting C, I'm doing from C to A plus B. So that would be, I'll just put A to label A plus B minus C, this vector here. The other way to do that, draw A, draw B, and then draw C backwards, draw negative C, and then connect from start to finish. I didn't do that nearly at the same scale. Let me see if I can do it at the same scale as before. So there's A, there's B, draw C backwards, connect from start to finish, and this vector should be, in theory, if I was drawing everything to scale, the exact same as that vector, and I'm not drawing it to scale. It's close, but not quite. So 2 ways to do that. So for part B, so all of this are 2 different ways to draw part A. For part B, A minus 2B, so I can draw A that way, we'll say. I can draw B. I can draw it twice as long in the opposite direction and have them tail to tail because I can just draw it twice as long in the same direction, but have them tail to tail. So there would be A, there would be 2B, we'll say, twice as long, same direction as B above. And then if I connect from 2B to A, that would be A minus 2B there. That's one way to get that vector. The other way is you draw A and you draw B twice as long in the opposite direction. So that would be minus 2b. And since I've drawn it as a negative, I'll connect them head to tail, because now I'm doing a plus negative 2b. And I should get the same kind of resulting vector as before, just in a different place on the page, but location doesn't matter. So 2 ways to draw that one as well. Oh, C looks fun. Okay. Negative 2a. So I'm going to draw something twice as long as a in the complete opposite direction. So we'll say that that's that. Then we're going to add 4c. So c is going off to the right. And we're adding, so we're drawing head to tail, off to the right. We'll say 1, 2, 3. We'll say that's 4c as best we can. And then we're going to add b to that. Oh, I got to go down this way. That's unfortunate. So we'll say that. And then if I connect my answer vector, connects from the start of that to the very end of that train. So from there down to there would be negative 2a plus 4c plus b. Something like that is what we're going for. Okay, Captain Sully, who landed the plane on the Hudson, is flying his plane 400 kilometers an hour in a northwest direction, and he encounters a wind that is blowing 80 kilometers to the northeast. So if he makes no adjustments, what's his new velocity? So for part A, so Captain Sully, north, south, west, east, is flying 400 kilometers in this direction. And to that, we're now going to add something 80 kilometers an hour, heading northeast instead. And so the resulting, the new speed, connects from the head of that to the tail of that. It's his speed plus the wind speed. I'm going to write the 400 on the other side so that it's not gumming up my picture anymore. There we go. So we've got those two sides. To figure out the new velocity, we need both how fast he's going and which direction he's going. So this is northwest, this is northeast. Those two directions operate 90 degrees to each other. Northwest and northeast are off by exactly 90. One's 45 east of north, one's 45 west of north, so they would be off 90 degrees to each other. So our velocity vector, our new resulting velocity, if I wanted to know how fast he's going, I would just want the size of that vector is how I would write that, so the magnitude of his new velocity. And since it's a right triangle, I can just do a Pythagorean theorem and get an answer without a calculator. Let's see. Get my phone out, I guess. Just super annoying. So the square root of 166,400. And then .9 kilometers an hour. So with that wind thrown in the mix, he's actually speeded up a bit. So that's the new speed, but it did ask for velocity. So we'll want to figure out this angle here, because that's sort of how far off of northeast he's now traveling. So that angle here, so the tan of that angle is 80 over 400. Well, let's see if I can get that in my calculator. 80 divided by 400 is 0.2. That's nice. It's about 11 degrees. So that's 11 degrees. If I draw my compass on here, there's west, there's north. Since that was exactly northwest, that's 45 degrees. So I could say I could say west, 56 degrees. I don't know why I'm putting those brackets. To the north, 45 and 11 up to the north. That's acceptable for me. If you take physics, sometimes they always want you to do the angle smaller than 45. So you would do 45 minus 11 and get 34, I believe that would be. So you'd say north 34 degrees to the west. Those are the two options for that. Okay, that was part A. There's still a part B. I was excited. I thought I was done, but I'm not quite done. What heading, so instead, that's knocking him off course if he makes no adjustment. And so we don't want to do that. We want to keep heading northwest because that's where they wanted to go in the first place. So Captain Sully, being a great pilot, knows how to make that adjustment. So what we're going to do is we're going to draw that same sort of picture, but we want the result of the two vectors to be on that northwest path. So the wind is still traveling 80 there. So they're going to have to steer into the wind a bit with their 400 because that's how fast the plane goes with no wind. They're going to have to adjust off of this to get to this path now. So we got to figure out, again, I drew it so it looks kind of the same, but really what I'm doing is rotating that 400 degrees, rotating this side here, out here, so that the resulting vector ends up on that northwest path. So we've got to figure out an angle in this picture. And in this picture, even though I've drawn it terribly, I believe this is now the 90, because this is supposed to be northwest, and this is supposed to be northeast. So if I drop my compass in there, that would be 45, and that would be 45. So the 90 is now on that side of the triangle. So that's our velocity vector over there. If I wanted to know the size of that velocity vector, again, it's a Pythagorean theorem, but now 400 is the hypotenuse. So that's going to be the square root of 153,600. So the resulting velocity is 139.9 kilometers per hour, the speed, I should say. I don't even think it asked for that, but I found it anyway. What heading should they take to continue? So we need to actually just figure out this angle. We didn't need that speed at all. And that speed, so now 400 is the hypotenuse, 80 is the opposite, so now it's sine of theta equals 80 over 400, which means theta is the inverse sine of that. So the inverse sine of 0.2, I believe that was. And I get 11.5. If I'm rounding off to whole degrees, I guess I'll call it 12 degrees. So that's to the west of northeast, if that makes northwest, sorry. So this full angle is 45 from north to northwest. So that would make this 33 degrees. So therefore, he should head west 33 degrees to the north. And then the wind will push him back onto that perfect northwest path. It's going to slow him down a bit because he's now just sort of steering into the wind, and he ends up only traveling 391.9 kilometers instead of if he goes kind of with the wind on the other direction, the wind speeds him up a bit. So there we have it. There's some questions. That's what adding and subtracting and scalar multiplication looks like with pictures. So some consolidation questions you can try and answer and fill out to make yourself a little note, and then no exit card, it looks like, right into the practice that you can work on in class.